So domain and range can be a bit tricky to understand what it's asking you at first, but once you get the hang of it, it's really as straightforward as asking yourself, where does this function show up? That's really all this domain and range stuff is about. So to spell it out more specifically, domain are the types of x values you can put into a function. So that's describing the input that's acceptable. So domain is the list of acceptable input. So, for example, you wouldn't try to put a negative number into a square root because you know that's not going to work. You can't have the denominator of a rational function be 0 because you're not allowed to divide by 0. And you can't put 0 or a negative number into a logarithm. So those turn out to be the three functions that have limitations on what you can put in. So they're the only functions that will end up with curious statements when you do their domain. So when it asks you that, it's asking you basically what kind of things can I shove into this function and still have it work. The range, it's the same idea, but instead of the input, it's talking about the output. So the range will be the list of possible outputs. So a square root, or sorry, a parabola, for example, squaring, you can't get a negative number as an answer if you've squared something. So there'll be a limit on the range of a parabola. A radical, the square root, never returns a negative number. So again, there'll be a restriction on what types of answers you can get out of that type of function. So we're going to do this one here first. There are two tactics you can employ to determine the domain and range of a function. You can remember lots of facts about how the function works, what it accepts, what it returns, and then use some logic in order to determine that based on a transformed and translated function. Or you can just sketch it and then look where the function shows up. So I'm going to do that for this one first. This one here, if you see the floating square up there, this is a parabola. It's been shifted to the left 4 and down 5. It will only be half as tall vertically as it should be, and it will take a third of the time, or the x's are only a third of as effective, so it's going to take thrice as long to get there. So there'll be a stretch horizontally. So if I pop this up here, put it on my untranslated axis, and if I translate the y-axis 4 to the left, 1, 2, 3, 4, and down 5, 1, 2, 3, 4, 5. There are my new crosshairs. So anything for a parabola, anything on the origin stays right where you leave it. This dot here, 1 and 1, should be half as high but 3 times as far. This one here, half as high, 3 times as far. 2, 4, that would be half as high, 3 times as far. 2, 4 would be half as high, 3 times as far. 2, 3, 1, 2, 3, 4, 5, 6, 7, 8, 9. That would be half as high, so it would be 4 and a half. 1, 2, 3, 4 and a half. And 3 times as far. 3, 6, 9. So I end up with a parabola that does this. Something like that. All right. Now, as I look at this particular sketch, I'm going to write the domain statement for it. So I'm going to say it in English and write it in code. So hopefully you should take notes about exactly what I'm saying in English so that you can understand these symbols later. So first thing you write is D for domain is a set of x values such that. Now I have to look at the x values here. If I look at this parabola, I ran out of room going that way, but if I were to slide the graph over and keep drawing, this parabola would continue that way forever. There's no reason to stop drawing it except that you run out of paper. So that's going to go forever in that direction. In this direction, it's the same thing. There is no value for x that you can put into this function where it would fail. It's always going to return an answer to you. So for this particular function, this parabola, there is no limit on what type of x values you can put in. So the only thing I have to say here for the domain is that those x values need to be real numbers. That maybe doesn't mean anything to you. There are a thing called complex numbers, which you'll learn about later if that becomes important to you. So for this function, because it is unrestricted, the domain is the set of x values such that those x values are real numbers and set. And we're done. That's the domain of this particular parabola. If we go to write the range, before I start writing it in code, I want to look at this thing. Range is a vertical question. You notice that this, from this vertex, it's going to go up forever. And you notice on this side from the vertex, it's going to go up forever. So this parabola, if I scan, look, if I walked upwards, looking left and right up here, I'm going to see that parabola somewhere. But you notice that it never goes below -5. It never goes below the vertex. That's a parabola thing. So when I go to write this range, write the list of possible outputs, I can't get -8 as an answer from this function because the lowest it goes is -5. So when it asks me what possible outputs are there, well, the answer is anything as long as it's above -5. So I'm going to start writing that out then. The range is a set of y values such that, now these y values, they have to be bigger than -5. So I'm going to put that in there. Y has to be greater than -5 because they are all above that line, right? You pop in the line y equals -5 and this parabola is always above it, except for one place, right there. At that spot, at the vertex, the parabola actually touches -5. So it's not just greater than, it's greater than or equal to, that didn't show up, or equal to -5. And they must be real numbers. So that's it. You're just looking at the graph of this thing and trying to decide where it is on the picture. So if it's everywhere on the x-axis, if there's no asymptotes or gaps in the graph, then the domain is unrestricted. If the range has a maximum or a minimum, you're going to have to put a comment on that somewhere in there. All right, now, if you want to do this algebraically, you're going to have to think about the restrictions of functions. So first off, for a parabola, if you go back to the functions catalog, or you think about parabolas in general, there are no restrictions on squaring things. You can square anything. Even complex numbers can be squared. It doesn't matter. You just execute the algorithm. So because there are no restrictions, then you just know to write this as your domain. Now you have to have that memorized. Like, you have to understand that about parabolas if you want to do it that way. And if you can remember that, no problem. It's just a fact. If you need to deduce it though, like if you look at this one, like, I don't know, if you don't know that fact, you're going to have to try the graphing method, because it's the only way to really show what the domain is that you can convince yourself before trying to convince anyone else what the domain restriction should be. So as far as the range goes, you might say to yourself, a parabola, an upright parabola, is always greater than the vertex. Greater than or equal to the vertex. Okay. So if I write that statement down, then 1/2 of 1/3 x plus 4 squared minus 5 always has to be greater than or equal to wherever the vertex was. So I can write that down. Notice that this thing, that's the function. Well, that's the restriction that I just parked in there. So if you want to go directly to that, if you know this fact, that a parabola is always greater than its vertex, then just find where the vertex is, park it in, and you're done. So for this next one, I'm going to try and find the domain and range of this logarithm, base 10. So I'm going to start with a sketch, because I think that's the most intuitive way to hunt for these things. So put in my unadjusted or untranslated axis. And this particular logarithm has been moved 4 to the right and up 5. That's a 3. So it's moved 3 to the right and up 5. Three, 4, what's the difference? 2, 3, 4, 5. All right. So the basic pattern for a log has a dot right here, and this particular one has been moved 4 times higher than it should be. It's been reflected vertically, and this 2 here makes the x's twice as effective, so it should have been shrunk closer to the y-axis. It gets there faster in half the time. So this dot here, it's not going to get moved up or down, but it is going to get here twice as fast. The next dot would be at 10 on the x, 1 on the y. So if I flip that underneath, because of the vertical flip, make it 4 times as far, 1, 2, 3, 4, and half in x would be only 5 squares, 1, 2, 3, 4, 5, and put it right about there. So instead of over 10 up 1, it's only over 5 down 4. So there we have it. This dot at 0.1 and -1, I have to flip it, make it half as far, and then 4 times as tall. I will put it here. So I end up with this logarithm like so. All right. It's that nice vertical asymptote there. So if I were to try and write down the domain statement for this, you get the front part for free, so you don't really have to think about it. It's always the domain is a set of x's such that, then I have to think about the conditions. So if I look at the x's here, do you notice that the function is fine? Like it's over here, it's minding its own business, it's being a function, doing function things. But as soon as I hit this dotted green line here, my translated y-axis, it doesn't exist anymore. Once it hit this vertical asymptote, it stopped being a function. It doesn't exist below x is 3. So that's the restriction on my domain, that this thing only exists, it only works for x values that are bigger than 3. So if I write that in there, x has to be greater than 3, because that's where I'm finding it. Now, sometimes this is just a greater than, sometimes it's greater than equal to 3. So I'd have to look at this thing here. If it's an asymptote, it never touches that line. It gets very close, but it doesn't actually reach it. So you can have any number that is bigger than 3, but it can't be exactly 3. So I'm going to have to leave this as a greater than, because this curve never actually touches that line. Close her off with the generic statement, it must be a real number, and we're done. As far as range is concerned, well, these are g values such that, well, it goes up to forever that way, and it's going to eventually drop to forever that way. There's no limit to what you can get out of this function, so there are no restrictions, except that they must be real numbers. Alright, now if we were to try and do this algebraically, logarithms, if you look back at the function catalog, have no range restriction. You can get a negative out from a log, and you can get a positive out from a log, and they go all the way up to negative infinity and all the way up to negative or positive infinity. So you just have to know this, if you know it, and you're not going to try and graph. As far as the domain is concerned, there's a thing about logarithms where everything in the guts has to be greater than 0. So if I write that down, that 2x minus 3 has to be greater than 0. Because a logarithm can't work on 0. If you try it in your calculator, log 0 is an error, and log of a negative is an error. So if I've got this little statement here, I could divide both sides by 2, and I would get x minus 3 has to be greater than 0. And I could pop the 3 over there, has to be plus 3. Well, there's that restriction that I put in there. So you can use the features of functions, recognizing that the guts of a logarithm have to be greater than 0, write that statement down, and then manipulate it with algebra until you get to here. That will work. Or if you can't remember this fact and can't remember this fact, because this was the memorization one, then just sketch it and see where the function exists on the grid. Alright, so we'll try this on a rational expression. These ones always throw people because they don't look like your normal functions. So this thing is just a 4 multiplying 1 over 3 times x plus 2. So you can see your a values out there in front. Your k value is there inside the operator, and then I have my translations there. Another way of writing this function that maybe makes it a bit easier to see that is if instead of writing it 1 over something, if you use the exponent -1 notation. So just maybe you remember that 1 over 3 is the same as 3 to the -1. So instead of writing it like a fraction, I'm going to write this as a negative exponent. So this thing would be 3x plus 2 to the exponent -1. So that's maybe a little more familiar for formatting. This out of the way. Oh, and I have not erased the last graph. So we're just going to chirp about this a little bit while I try and do that. I'm not very good at doing two things at once. So that thing there, that's a rational expression. And rationals are the ones that do this. Right? They have a vertical asymptote and a horizontal asymptote. This one has been moved 2 to the left and up 1. It should be 4 times taller or deeper. Like, so it should be 4 times further from the translated x-axis than it normally would be. And this 3 here makes those x's more effective, so it should get there in 1/3 of the time. Yeah, okay, good. So let's try and sketch that thing then. So with my untranslated axes, I need to translate them 2 to the left and up 1. In the basic pattern, there's a dot here at 1 over 1 up. So that thing needs to be 1/3 of the way, so that's going to squeeze it closer to the axis here, and then 4 times higher. So instead of 1, it's 1, 2, 3, 4. In the basic pattern, there's a dot here at -1, -1. And that thing should be 1/3 of the way and 4 times further down. So instead of 1, it's 1, 2, 3, 4. There should be a dot here at 2 over 1/2 up. So if I make that 1/3 as far, that's about here, and 4 times further up would be here. So that same dot will happen. 2.5 would be 2/3 and 2. Next pattern would be 3 out, 1, 2, 3, and up 1/3. Quadruple that height would make it 4/3. Cut the distance over in 1 would be 1. So I get something like that. So I'm getting this rational function with its horizontal asymptote here, spiking up to the vertical, and a vertical asymptote here, smoothing out to the horizontal asymptote. That was terrible. This is an embarrassing sketch. You will, of course, do much better than this one when you're doing it yourself. Okay, so if I were to look at this thing horizontally, notice that if I'm walking on this blue line here, I can see the function above me everywhere until I get to this spot. And once I'm over that spot, I can see the function under me everywhere, just not at that spot. If I were walking at this place where x is -2, if I look up, that function is infinitely tall. So I can't see it. It's not above me. If I look down on this side, it's infinitely low. So it's not below me either. Well, this function will accept any value except that one. So it can't be -2 because of this vertical asymptote. Now, if you remember the logarithm we just did, it couldn't be a specific x value because of its vertical asymptote. Well, that's the same here. Anytime you see a vertical asymptote, you're getting a restriction on the domain somehow. So in this one, because it can't exist here, the domain of this function is going to be a set of x's such that, well, the only value that's not allowed is -2. So I'm going to write that x cannot equal -2. But it can be any other real number. Now, when I go to do range, the range is going to look very similar. If you look up and down on this thing, it's if I travel up here, it's over on my left, then it's over on my right. But at this particular value, at 1, there's an asymptote. And so this function never actually touches a y value of 1. So the range value here, or range statement, would be it's a set of h's such that those h's are never 1, but they can be any other real number. So there you go. Alright, so we have a sine function here in order to do our last example. So I'm going to sketch it, take a look at where it is, and then write the domain and range statements from there. So if I put in my untranslated axis, and I'm going to use the funny pi scale where I leave 6 squares for pi. 1, 2, 3, 4, 5, 6. That's pi there. And 1, 2, 3, 4, 5, 6. That's negative pi. So to make the y-axis not too distorted, that would be 1, 2, 3, and negative 1, negative 2, negative 3. So this particular one has been shifted left, pi over 3. I have left 6 squares for pi, so a third of that would only be 2. So I'm going to pop this in, translated 2 squares to the left. And it's been moved down 1 unit, not 1 square, 1 unit. That's here. Alright, now this thing has been stretched thrice as far from the translated x-axis. So signs usually go up 1 and down 1. So if I make it 3 times bigger, it should be max 3 up, max 3 down. So I'm going to pencil in that top end here. 1, 2, 3 units up. And 1, 2, 3 units down. Alright. And a sine curve usually takes 2 pi to complete 1 cycle, but this one is twice as fast. So if it's twice as fast, it shouldn't take 2 pi, it should only take 1 pi, meaning you'd fit 2 full cycles into your 2 pi window. So I'm going to draw a little scaffolding every pi units so that I can clip off the pattern. And pi is 6 squares on this particular grid. So 1, 2, 3, 4, 5, 6. There's that. 1, 2, 3, 4, 5, 6. Here we go. 1, 2, 3, 4, 5, 6. Etc. And a sine curve starts low, or starts in the middle, sorry, ends in the middle, is in the middle, peaks halfway between those, and troughs halfway between those. So repeating the pattern, middle, 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 peak, trough, peak, trough, peak, trough. And I just have to sketch it in. Oh. This is not pretty. This is a close enough for horseshoes and hand grenades kind of graph, but it'll do. So the whole point of that was to sketch the domain or state the domain and range. So before I write the domain statement, this wave keeps going forever. So it never stops in that direction, and it never stops in that direction. So this function continues going forever in both directions, which means it will accept anything on the x-axis. And again, if you think about the other ones that did have restrictions, the domain restrictions either had a gap or they had vertical asymptote, and this has neither. So there should be no restrictions on this domain. It will accept any real number. Now the range, on the other hand, is different. You notice that this thing never returns a value higher than 2. Right? It's never up here. It stops at 2, and it never goes below -3. Sorry, it never goes below -4. So these values, this curve is pinched between -4 and 2. So when I write the range for that, it's a set of j's such that, well, -4 is less than that j, which is less than 2. So it's pinched between these two values. You need to ask yourself, does it ever actually equal -4? Well, it does. It does here and here and here and here. It's actually equal to that, so I'm going to acknowledge that. And here and here and here, it's actually equal to 2, so I'll acknowledge that as well. And then finish her off with those j's need to be real numbers. And we're done. So when writing your domain and range statements, it could be that a certain x value must be greater than or less than. It could be greater than or equal to. So you're looking at these, or these, or not equal to. Or you may get to pinch between some number like this. It all depends on which functions you're working on.